In the last class we were looking at spectral theorem for a finite family of commuting normal operators. So, the first step is to prove the Fuglede's theorem, which means that, which says that if T is a normal operator and x is a bounded operator which commutes with T, then x also commutes with T star. Okay. This requires that T is normal. In general, this is not true, but for normal operators commuting with T will imply commuting with T star, and once it commutes with T and T star, it will commute with any function of T, right. So, it will commute with polynomials in T and T star, and so it will commute with all operators coming from the continuous functional calculus, and then you can extend it to all bounded functions, and then you will see that x commutes with f of t for any f bounded, in particular all those projections you get from spectral theorem, and these are equivalent, right. So, that is what we will prove first, and once we prove that the projections of commuting normal operators will commute, and then we can repeat the arguments for the self adjoint case and develop the continuous functional calculus or the spectral theorem and so on. Okay. But we will deduce it from the self adjoint case. We are not going to write down the Riemann sums again and things like that. Okay. So, let us continue. So, we were into proving Fuglede's theorem. So, let us just quickly look at what we did so far. We defined exponential of a operator. So, we had the exponentials commuting if the operators were commuting, and since T is normal, it follows that exponential of e to the I lambda bar t plus lambda t star is the product, because T and T star commute, and since T x equal to x t, we get that for all polynomials in T, x will commute with that, and so we can write it for exponentials as well, right. So, this is what we had. So, in other words, x will be equal to e to the I lambda bar t times x times e to the minus I lambda bar t. Then we define this function f of lambda equal to e to the I lambda t star x e to the I lambda t star, and then we substituted this identity for x here, and we had and we combined this, right. So, we had a unitary operator here and a unitary operator, the adjoint of that, right. So, that was unitary because if A is a self adjoint operator, e to the I A is unitary, and lambda bar t plus lambda t star is self adjoint, and so e to the I lambda bar t plus lambda t star is unitary. Because of that, the function f lambda, so f lambda is like this, right. So, here I have this unitary, so call it u, then I have u x u star. So, its norm is simply the norm of x, and so f lambda's norm, operator norm is norm x is a constant. Okay. Now, the claim is lambda going to f lambda is entire. So, remember f lambda is defined for all lambda in x, and lambda going to f lambda is entire, and it's bounded, right, because its norm, the operator norm is bounded, and so it is constant by Liouville's theorem. So, we have to justify this. So, let us recall what is meant by lambda going to f lambda is a holomorphic function. You form these for each vectors u and v, you form lambda going to f lambda is an operator acting on u inner product with v, that is holomorphic in the usual sense, right. That is the definition of holomorphicity. In fact, all the definitions you may come up with are generally equivalent if you have Hilbert space and so on. Okay. So, we will justify the claim. So, so the claim, so let me write that lambda going to f lambda is entire, and norm f lambda, well, this is equal to norm x, and so bounded implies f lambda is a constant, Okay. so its an entire function is sort of trivial because f lambda is written. So, let us go back to f lambda. Here is the expression for f lambda. F lambda is e to the I lambda t star x e to the minus I lambda t star, right. So, let me write that f lambda is equal to e to the I lambda t star e to the I lambda t star times x e to the minus I lambda t star. So, why is this an entire function? What do I mean by it as an entire function? You look at f lambda acting on u inner product with v, right, and you want to know if this is holomorphic in lambda, right. Well, these are exponential functions, and so they have power series expansion, and you will get a power series expansion in lambda, right. So, you can write this as summation, summation lambda to the k, well, let me not write the coefficients. So, I will have lambda to the k and some operators, right. So, let us write the operators first. Some operators here, those are the coefficients, and I will have lambda to the k, right. So, since it is a power series expansion and it converges in the operator norm, it is trivial to see that if I look at something like this, I will have the operator coefficient at k acting on u inner product with v times lambda to the k. So, it gives me a power series expansion which is valid for all lambda, right. So, this is true for every lambda in the complex plane, and so it is a holomorphic function, right. It is an entire function. So, the entire part is that it is an entire function is more or less straightforward, and because we wrote this f of lambda as some unitary times x times the adjoint of that, the norm is the norm of x, right. So, it is a bounded function. Now, if I have an operator valued bounded holomorphic entire function, why is it a constant? So, we know this for complex valued functions via Liouville's theorem. So, let us justify that. Okay. So, that is the next thing. So, then we will see that f lambda is a constant. So, so look for each u v, consider lambda going to f of lambda acting on u inner product with v. Okay. So, that is an entire function, and f lambda is bounded in the operator norm, right, with respect to lambda. So, so this function, so modulus of f lambda u v, this is less than or equal to norm x is some constant, right, some fixed constant, norm u, norm v, right. So, for every lambda in C, right, but it is an entire function in lambda. So, it is constant, right, by usual Liouville's theorem, right. So, by Liouville's theorem, f lambda, so lambda going to f, so this function lambda going to f lambda acting on the vector u inner product with v is a constant, but the constant depends on u and v, right. So, let us write f lambda u v. Of course, it depends on u and v, but it will not depend on lambda, right. As a function of lambda, it is a constant. So, this is let us say q u v. So, q u v is some number, some complex number, but it is a constant with respect to lambda, right. So, now you can think of q u v. So, this is going to be a map from h cross h to the complex numbers, and you see that it is linear in u, right. Because of this, if I change u1 u to u1 plus u2, it splits, right. Similarly, v it splits and the constants will come out and so on. So, it is a sesquilinear form, right, sesquilinear form and bounded, right, and mod q u v is less than or equal to some constant times norm u, norm B, right, because f lambda has bounded operator is bounded. But this we have seen already, if you have a skew linear form which is continuous, that means it has this estimate, then it is given by an operator, right. So, there exists an operator. So, there exists A which is a bounded operator such that Q U V is given by inner product of A acting on U in with V, right. So, this we know, and but this is supposed to be f of lambda acting on U inner product with V, right, but that is the definition of Q. So, this will tell me that, so this is true for all lambda, right. So, for every lambda in C, hence f of lambda equal to A, right, for every lambda. So, that is what we mean by f is a constant, right. So, a bounded holomorphic function, bounded entire function, even if it is taking values in operators, as long as it is an entire bounded function, it is a constant. So, there is a fixed operator A such that f lambda equal to A for every lambda. Okay. So, now we can go back to the expression for f lambda. So, recall that. Okay. So, recall that f lambda equal to, well, f lambda we started with one expression for f lambda and then brought in something else. So, that we had those unitaries and so on, right. So, let us do that. So, let us rewrite this f lambda as e to the I lambda bar t plus lambda t star, right, x times e to the minus I lambda bar t plus lambda t star, right, the same operator. So, that is the self adjoint operator, and you have something like e to the I A x e to the minus I A, right, where A is self adjoint. So, this is my constant operator, right, this is constant with respect to. So, what we have proved is this is a constant operator, constant with respect to lambda. So, we can differentiate with respect to lambda. Remember, this is an entire function. Now, I am not going to write down this in full detail. If you are not comfortable differentiating operator valued functions, you can act it on a vector, take inner product with another vector, go to complex plane. So, that you have a function which is defined on complex plane, taking values in the complex plane and differentiate in the usual sense. Okay. So, you will get the same thing. If you have differentiated matrix valued functions, then it is essentially the same. Okay. So, differentiate with respect to lambda on both sides, So, the left hand side gives me 0 because f is constant with respect to lambda. Right hand side you have to apply product rule, right, because it is the product of two functions. Also remember there is some lambda bar, but we are taking the derivative with respect to lambda. So, this is the usual holomorphic derivative of the function of the holomorphic function f lambda. So, lambda bar will not give you anything, okay, right. It is like if you differentiate with respect to z, that is the holomorphic derivative, z bar differentiated will give you 0, right. So, that is so 0 equal to, so f prime lambda is 0, f prime lambda is 0, this is equal to, well, I have to differentiate. So, this is a product rule, I have the exponential of something, right, and the lambda comes with t star. So, if I differentiate that, I am going to get t star, right. So, I will get I t star e to the I lambda bar t plus lambda t star. I am not very careful in writing the order properly because everything commutes here, t and t star commute. So, whether I put the t star on the right hand side or the left hand side of the exponential does not really matter. Plus, well, I should have okay, sorry, I should be using the other expression. So, let me rewrite this. So, So, instead of we brought in the unitary only to say that f lambda is bounded, but we will use the original expression which is e to the I lambda t star x e to the minus I lambda t star, right. So, that it is clear that it is entire in lambda, you expand it, you will see that it is entire in lambda. F lambda is constant. So, when I differentiate with respect to lambda, I get 0, right. But the answer here is you do the usual product rule. So, I will get I t star downstairs and e to the I lambda t star, right. So, you can check all this in the usual sense, taking a vector u and taking inner product with v and looking at it as a function from the complex plane, taking values in the complex plane and differentiating in the usual sense. In any case, you can write down the power series and you see that this is what will happen. So, I t star times e to the I lambda t star, that is what you will get if you differentiate the first term, right, e to the I lambda t star times x times e to the minus I lambda t star plus, well, the first I lambda t star, x has no lambda. So, there is no differentiation with respect to x happening, think of x as some constant. In the next one I will have e to the minus I lambda t star and minus I t star, right, that is the thing on the top with lambda. So, that comes down when I differentiate with respect to lambda. Okay. So, put lambda equal to 0, we get, well, what do we get if you put lambda equal to 0? In that identity, if you put lambda equal to 0, I get 0 equal to. So, lambda equal to 0 here will give me identity, here also it will give me identity. So, I have I t star times x. Similarly, this is identity and this expression is also identity, and I have minus I t star. I is there, so I can cancel the I from both sides. I will simply get t star x minus x t star, right. So, that is same as saying x commutes with t star, right. So, t star x is equal to x t star. So, x commutes with, so x commutes with t star. So, we started with t a normal operator and x commuting with t. We proved that x commutes with t. So, there are several other proofs of this. Okay. So, this is one such proof where I could introduce some entire function which is taking values in the space of operators. Okay. So, that is why we did this and this tells me that if you have a commuting, if you have an operator which commutes with a normal operator, the first operator also commutes with the adjoint of this normal operator. And so, in this case x commutes with t, x commutes with t star, x will commute with any function of t, whether the function comes from continuous functions or bounded functions. In particular, x will commute with all the projections. We will apply this for commuting normal operators. So, if I take t and s normal and if t and s commutes, then t will commute with s star, s will commute with t star, and both t and s will have the property that it commutes with the function of other operator. In particular, the projections associated with t and s will commute. Okay. So, let me write one remark because we can use this. If x commutes with t, if x commutes with t where t is normal, okay, then x t star equal to t star x, and so this is something we have done. You look at the C star algebra generated by t and t star and identity, x will commute everything there. That is the continuous functional calculus, and then you can go to bounded functional calculus, right. So, f of t for any bounded f, right, for any bounded f. Okay. So, function bounded on the spectrum of t. Okay. So, let us continue. So, now we can write down the spectral theorem for commuting normal operators. Okay. So, theorem, okay. let us see if I have different versions. So, I will write only one version because it is you can think about the continuous functional calculus and so on. Okay. So, let A1, A2 etcetera an. So, I have n commuting normal operators, bounded normal operators, B bounded commuting normal operators, on a Hilbert space H, right. So, we will do the cyclic vector case first and then you can take the direct sum. So, I will do only the cyclic vector part. So, let V be a cyclic vector. What does that mean? You hit V with all the polynomials in A and A star and so on. See, all those polynomials in A, Aj and Aj star will make sense because everything is commuting now, right. It is bounding commuting normal operators. So, A1 commutes with A2. So, it will A1 commutes with A2 star, A1 will commute with any polynomial in A2 and A2 star and similarly the other way. So, writing down the polynomial in Aj and Aj star makes sense because they all commute with each other. So, there is no problem and you can hit V with all these polynomials in A star and take the span closure, that is the smallest subspace containing V invariant under both Aj and Aj star, right. Let V be a cyclic vector, that is the smallest subspace closed, of course, closed subspace containing V and invariant under both Aj and Aj star for every j, right. So, this would be, you look at the so is equal to the whole Hilbert space, okay. That means, so let me write it down here. So, you look at all polynomials in Aj and Aj star and so A1 to the L1, okay, A2 to the L2 etcetera an to the ln. In the self adjoint case we had only this because the adjoint is itself, right, but in the normal case you also have to put the adjoint. So, I will put A1 star to the M1 etcetera an star to the Mn, right, and you look at V. So, you look at the span closure of this. Okay. So, look at the span. So, this is contained in H densely, right. So, that is what you mean by V is a cyclic vector. Okay. So, in the cyclic vector case you have a measure and you have multiplication by Zj's, right. So, containing Aj, then there exists a measure, mu on where is the measure. So, this is going to be on norm Aj comma Aj. So, this is a closed interval, you look at the product of this, okay, sorry, this is the normal case. So, I should write this as a domain in Cn, right. So, you look at measure on product j equal to 1 to n Zj, the Zj is such that real part of Zj is less than or equal to norm A, norm Aj, and imaginary part of Zj is less than or equal to norm Aj, right. Remember, for one operator this is what we had, right. It was something inside the complex plane, but this is sitting inside Cn now, okay. So, there exists a measure and a unitary operator and a unitary u. So, where is the u from? U is from the Hilbert space H to L2 of this product space. So, product j equal to 1 to n. So, I let me not write the whole thing again, it is this set comma the measure mu, right, such that the operators A j becomes multiplication by Zj, right. So, such that U A j U inverse, right. So, U inverse takes L 2 to the Hilbert space H, A j will take H to H, U takes it back to L 2, right. So, I take a function f there. So, that is a function on L 2 on the product space at the point Z, Z is Z 1 Z 2 Z n, right. This is equal to Z j f of Z, right, because f is in L 2. So, Z is simply Z 1 Z 2 etcetera Z n, right. So, if you have a commuting family of normal operators, say finitely many, then with a cyclic vector you have this. If you do not have a cyclic vector, you generate you take one vector, look at the cyclic subspace generated by that vector and then these operators, and then take the direct sum, right. This we have seen in the case of single operator. Proof is the same for. So, we will look at only this one. Okay. So, let us prove this. Now, we have done most of what we want. The only part which was missing was this commuting thing, right. Whatever is written down should be commuting with each other, and we will reduce everything to the self adjoint case and use the previous result. Okay. So, let us prove this, right. So, write each A j as the self adjoint parts, right. So, this is B j plus I times C j, right. What are B j's and C j's? So, as in the case of the single normal operator, B j is simply A j plus A j star divided by 2 and C j equal to A j minus A j star divided by 2 I, right. So, both B j and C j are so B j C j are self adjoint, okay. And whatever operator you take A1 to B1, B2, B3 up to Bn, C1, C2, C3 up to Cn, there are 2 n self adjoint operators, they all commute with each other, right. That is the content of the Fuglede theorem. Okay. So, by Fuglede theorem, I look at B1 C1, B2 C2 etcetera Bn Cn, this forms a. So, 2 n self adjoint operators, 2 n commuting self adjoint operators, right. 2 n commuting self adjoint operators, right. But that is precisely the content of the Fuglede theorem, right, because if A1 and A2, so let us just take 2 of them, A1 and A2 commute, then A1 will commute with A2 star, A2 will commute with A1 star, right, because both of them are normal. B1 C1 and B2 C2 will commute with each other, right. So, that is all I am saying. But once we have this 2 n commuting self adjoint operators, the result for the commuting family of self adjoint operators will tell me how they look like, right. So, by the earlier result, so also notice that we have the cyclic case, notice that if you look at the polynomials in B1, C1, B2, C2 etcetera, that is same as polynomials in Aj and Aj star, right. But that means we have the cyclic case for the self adjoint operators as well, right. So, notice that H is equal to span of or let me say simply write cyclic subspace generated by these operators B1 C1 etcetera up to Bn Cn for the vector V, right. So, this is the cyclic case of the spectral theorem for 2 n self adjoint commuting family of operators, right. So, 2 n many. So, by the earlier result, we have a unitary operator, we have a unitary U such that and a measure I should write that as well, right, and I measure mu. Well, where is mu supported on? So, supported on. So, you look at all those measures and look at the norms and look at form an appropriate set, right. So, I will just say L 2 of R n with respect to mu, where mu is supported on actually the 2 n product, right, of okay. So, I should be very careful in writing this. So, this is the Bj's, the norms of Bj's and Cj's, but they are all bounded by norm Aj, right. So, j for one okay. So, how do I write this? The notation becomes a bit complicated. So, let me write n here and I will write norm Aj cross minus norm Aj, right. With respect to Aj, there are only n many operators. When I write B and C, there are 2 n many, but norm B1 and norm C1 are bounded by norm A1, right. So, instead of writing with respect to norm B and C, we wrote generally with respect to norm of A, that is all is there, but this is sitting inside Cn, right, or R2n. So, strictly speaking I should say R2n, which is identified with Cn in an appropriate manner. Okay. So that well, where is the unitary u? U goes from the Hilbert space H to L 2 of this product space, which I will not write down again, to mu with u inverse, let us say, how do I write this, B Bj and u, right. So, f would be equal to, so one should be very careful in the index. So, what I mean is each Bj will be multiplication by xj's, but there are 2 n many, right. So, B1 and C1, so B1 and C1 I would say is multiplication by x1 and x2. So, that B1 plus IC1 will become multiplication by x1 plus Ix2, which is going to be my Z1. Okay. So, I hope that is clear. So, let me write it for 1 and 2, so that this is clear. B1 x equal to x1 times f at x is in R2n, and u, it is the same unitary, right. Okay. So, u C1 u inverse f x equal to x2 f of x and so on, right. So, you can write down for appropriate integers it is b, for the other complement it is c, right. So, which implies that u A1 u inverse f would be at x will be x1 plus Ix2 f of x, right. So, after appropriate identification, this will be Z1 times f of z, right. So, I have x1, x2 etcetera x2n minus 1 x2n, right. I am identifying this as Z1, Z2 etcetera Zn, where Z1 is x1 plus Ix2 and so on, right. So, that will tell me that the operator A1 is multiplication by Z1, operator A2 is multiplication by Z2 etcetera. And okay, so we will stop here. In the general case, so we stop with the cyclic case. In the general case, you have to take the direct sum. So, starting from one vector, you generate the cyclic subspace and you take the orthogonal complement and see that both subspace and the orthogonal complement are invariant under both Aj and Aj star. We have done this for a single operator, the same argument works, and you will get a direct sum. Okay. So, we will stop here for the time being.